Welcome back to Bio 6612. Today we're going to cover logistic regression diagnostics. And these are similar to diagnostics you learned about linear regression in 6611. And in particular, I actually find the Stats UCLA website to be really useful for understanding these diagnostics. And it's a good website in general, so I use it quite a bit. So one type of diagnostic tool is the residuals. And for logistic regression, there are two types of residuals that might be interested in: the deviance residuals and the Pearson residuals. And these are both useful for identifying potential outliers or misspecified models. So the deviance residuals measure the contribution of each observation in your data set to the deviance chi-square statistic. Basically, these measure the disagreement between the maximum of the observed and the fitted log likelihood functions. The Pearson's residuals measure the contribution of each observation to the Pearson chi-squared statistic. Basically, the relative deviations from the observed and the fitted values. And a good way of looking at these is to graph them against the predicted probabilities or the observation number. I tend to like to graph them against the observation number because that gives a interpretation for the residuals that's more similar to what you would get from linear regression, where you're looking for residuals that are randomly scattered about zero. Then there are several different statistics that you can calculate to identify influential observations in the data set. Influential observations are those that whose deletion have a large effect on parameter estimates. And you learn about these in 6611 for linear regression. And for the most part, you interpret them all the same way, where a large change in any of these numbers at a particular point or observation indicates that point is more influential. And I'm going to look at the DF betas, which tell you how much each regression coefficient changes when a particular observation is deleted, and the hat diagonal matrix, which is a measure of leverage or potential influence for each observation. But all of these can be potentially useful diagnostic criteria for influential observations. And to look at a couple examples, we're going to go back to the weight loss attrition data from the last lecture. And this example looks at the predictors of attrition from a weight loss program, where variables are complete, which is 1 if a user completed the weight loss program, or 0 if the user dropped out. Gender, age in years, BMI, and steps per day at baseline. Again, since we're interested in attrition, which is probability of dropout, rather than the probability of completion, after we load the data, we're going to refactor it so that completion is the reference category and dropout is the primary category of interest. And we're going to run a model with steps as the outcome because I want to see if I want to look for potential outliers in this model and influential points. So first we look at the Pearson residuals. And in general, when I'm plotting the Pearson residuals on the y-axis here against the observation number on the x-axis. And when I look at this type of plot, generally what I'm looking for is that the residuals are scattered around 0 in a roughly random fashion. So 0 is the dotted line here. And for the most part, that seems to be satisfied, except for these 2 points, which are much farther away from 0 than the rest of them. So those are potentially suspect based on this diagnostic plot. Deviance residuals are interpreted in much the same way. And again, looking at this plot, these 2 points are just farther away than the rest, so they're potentially suspect in this model. Next, we're going to look at the hat diagonal matrix. And this statistic tells you about the measure of leverage or potential influence basically how extreme the observation is in the predictor space. So I'm basically looking to see if any of these points are more extreme than any of the rest of them. I have the hat matrix diagonal value plotted on the y-axis, the observation value on the x-axis, and none of these points seem to be that extreme. So this actually doesn't necessarily agree with the residual plots in the previous slide. If we only looked at the hat matrix diagonal, we would probably conclude that there don't seem to be any potential outliers. So that would give us a reason to maybe look at another diagnostic criteria. Here we're looking at the DF betas. The DF betas tell you how much each regression coefficient changes when a particular observation is deleted. Here we have the observation number and then the DF beta for steps for the steps covariate, so like beta 1. And here beta 1 changes quite a bit if the first or the second point is deleted, but not nearly as much if the rest of the points are deleted. And similarly, this is the DF beta for beta 0. And beta 0 changes quite a bit if the first or the second point are deleted, but not as much otherwise. So this indicates that points 1 and 2 have higher leverage than the other points in the data set. So what do we actually do with this information in practice? Well, observations 1 and 2 could be true outliers because they do seem to be more extreme relative to the rest of the data. But on the other hand, this is a small data set. And DF betas and residuals agree with each other, but they don't agree with the hat matrix diagonal. And we have to be really careful about deleting points that are potential outliers because that can really change the interpretation and of our model. And we want to be careful not to just delete points because we don't like them to try to get to a model that we like better. So in practice, if you find evidence of influential points, it's good to report both results with and without potential outliers. And another sort of point that I like to think about is if the outliers are very clear outliers, say you have an entry for age that's equal to 5,000, well, clearly that's not biologically possible. So that point was sort of misentered. So I think it would be okay to delete that point. But if you have something that is still within a biologically plausible range, but is just different from the rest of the data, I would be very hesitant to delete that point because it might be just variation that's due to biological variation that you don't want to remove because it could make your model less reflective of what's real.